Welcome, ladies and gentlemen, here to the forum of the Hydrogen and Fuel Cell and Batteries Group Exhibit on Hannover Fair 2014. You're welcome to have a seat, to have a drink on the house, coffee or whatever you like, and follow the next interview here on stage with the CEO and Chief Scientific Officer of Cella Energy Ltd, Professor Stephen Bennington. Please give him a big hand.
Thank you.
Hello.
Hello.
And we'll be talking about safe, low-cost hydrogen storage, and that's it all about. And you brought some model with you. We'll talk about that later. Yep. But I will start about Cella Energy Ltd. It's a spin-off from the UK Government Science and Technology Facility Council, based near Oxford, UK, and was founded in 2011. You were working there, weren't you?
Yes, that was where my original post was.
So what did you do there? What kind of research work did you do there?
I was a material scientist, particularly in nanotechnology, but interested in hydrogen storage. But I also had a position as a visiting scientist, visiting professor at University College London, at their London Centre for Nanotechnology. And I was looking for ways of using nanotechnology in a cheap way to improve hydrogen storage materials, and that's where the project started.
So you were already sure about the hydrogen. Hydrogen is a perfect fuel, it's clean, it's abundant actually, but you can't dig it, can you?
No, it's not available anywhere naturally, so you do have to make it. So it's an energy store rather than an energy vector like gasoline or gas.
And there's a big disadvantage about hydrogen because it's so voluminous. You need a lot of space to store it. That's the problem.
Exactly. So by weight is extremely efficient, obviously, about 3 times the specific energy per kilogram of gasoline. But by volume, it's a real problem. So you either have to compress it to high densities or liquefy it at low temperatures. And neither of those two are perfect solutions for all applications.
Okay. So you found a new way to store the hydrogen. How did you do that? What is the way?
Kind of. I mean, it's more like an adaptation of existing work. I don't know if you know, but particularly in the United States, they were spending something like 1.2 billion on a program to look at different materials to store hydrogen in a dense way. And we sort of piggybacked on that work. We took the best materials that came out of that Department of Energy program, and we used nanotechnology to try and improve them to the point where they could actually be practical.
The idea is to use hydrates. Maybe some of us know metal hydrates. So you can put a lot of hydrogen in a small amount of material.
Yep.
And but this is in metal hydrates. It's heavy because it's metal.
Yeah.
But you have another material. What is your material?
Well, I mean, the 2 types of hydrides, basically. One is a metal hydride, and a metal hydride you can cycle to some extent. You can take hydrogen in and out of it. And the other one is the chemical hydride, and that's the one we focused on. Because there are chemical hydrides, and particularly the one we look at, has 2 or 3 times the amount of hydrogen per specific weight than a metal hydride. The complication with it is that you can't cycle the hydrogen in and out in hydrogen form. You have to go through a chemical process. So it's a chemical process to make it, and it's a chemical process to regenerate it after it's been used.
Let's talk about the material. It's ammonium boron?
Ammonia borane is the hydride we use.
Right.
And then we make a composite material with plastics, with polymers. So ammonia borane itself is a really nice material. It has a huge amount of hydrogen in it. But the problem is it melts at around about 100 degrees centigrade. So when you heat it up to drive the hydrogen out, it becomes a liquid. And then the hydrogen comes out. And so you can imagine it's like opening the top of a Coca-Cola bottle that you've just shaken up. So you end up with this huge foaming mess. And it's very difficult to package. And although people have tried in the past to use it, they all came across these problems. Yeah. But by combining it with the plastic, we've shifted its melting point way, way up. So it now just stays like a plastic material. It looks like a plastic. It's boring white plastic material which you can extrude or press or mold into any shape you like. And when you heat it up above 100 degrees centigrade to drive the hydrogen out, it stays the same. It doesn't change shape.
So I can remember, let's say 12 or 13 years ago, ammonium boron was already discussed very much as a carrier of hydrogen.
Yeah.
But the problems were too big, and you solved the problems actually.
Yes.
So you made a pellet out of it. You made a nano composite. How can I imagine that? So it's
just like a little plastic pellet. So you just think of any plastic bead. It's like that. It looks white. You can extrude it and then chop it into beads if you like. We have various different methods now of turning it into energy or holding it, and one method is a cartridge. So we can pack the material into a cartridge like this, and then we have a system which you can see on our stand, which use it like a gun, if you like. It has a piston which pushes it into a cell, which is at high temperature, 120 degrees C. The hydrogen then is released over a period of about 2 to 3, maybe 4 minutes if you want it slowly. And then that's ejected back out and dropped back into a magazine. So
but this is already the second generation, is it? That's the first generation, is that?
That's it, yeah, it's just like that.
Something like that.
Yeah, exactly.
Okay. The pellet looks like this one. So how much of hydrogen would fit into a pellet like this one?
About a litre. So, well, I mean, slightly more than that. But 1 gram is 1 litre of hydrogen.
Okay. Is it toxic?
That one isn't.
No, obviously not.
It's slightly toxic in reality. You can hold it in your hand, but it's the kind of thing you should wash your hands of afterwards. Okay. So it's slightly less toxic than gasoline, for example. So I wouldn't eat it. It would give you very bad wind. No,
that was a fake, okay? You can have that at the booth of
You
Cella
can get them
Energy.
from our booth, yeah.
It's very tasty. It tastes like chocolate, so no, it's not the material itself. Anyway, I would like to show you. Okay, these little pellets you could tank in your car. Yeah. That's the idea.
That's the idea. So ultimately, I mean, this is fine. So you can refuel something made out of these cartridges very quickly. Just pull it out, put another one in. But if you wanted to run a car, you need more than just 20 kilograms. You need something like 50, 60, 70 kilograms of material to run you the 600 kilometers. And that's too heavy to lift. You need a bit of pump it, like a fluid. So if you make it into small pellets like that, you can use a vacuum cleaner type technology. In the UK we have Dysons, and it's that kind of technology.
You don't need filters with Dysons.
The cyclone works beautifully. That's what we have a demonstrator we can show you. And then you can use that to pump it into the back of your vehicle. And then in your vehicle, you would have a little tiny version of that, pump it out of your little plastic storage tank into a hot cell. Hydrogen is evolved there because it's hot, into the fuel cell, and the fuel cell runs the vehicle. So
you have to heat it up, the little pellet, up to 100 degrees, that it gives the hydrogen free.
That's right.
Okay, so inside the car there must be some device to heat it up.
Yeah, so one little section of it is about 100 degrees C.
Okay, and then after you used all the hydrogen that were in the pellets, you have the empty pellets. You take them out via the vacuum cleaner and put new things in.
Exactly. So as far as a consumer is concerned, a customer, they would have 2 nozzles, not one. So it would feel very familiar. They have one nozzle which takes the pellet out and one which gives them fresh pellets. And then you use an infrastructure which is very similar to what you might be familiar with now. So you would have a tanker which will be delivering the fresh pellets to the filling station, and then the same tanker will take the pellets back to the refinery where they would get recycled.
But for this you need a completely new infrastructure if you really want to implement it.
Sure.
This will be pretty hard probably because they're building up the infrastructure now with compressed hydrogen at the moment, 700 bar. Why is your system better than the 700 bar system?
I mean, firstly, the infrastructural costs are much, much lower. So if you know that the compressor, if you're using a 700 bar tank in the back of your car, then you've got to have a compressor which compresses to 850 bar. And not only that, it's got to be simple and safe so that any customer can come and use it without any special training. And those compressors are expensive. The ones that run just for one car every few minutes is about $600,000. And the big ones are about $2 million. And you have to have several of those at every filling station. And so that infrastructural cost is something that the car industry does not wish to bear. They're hoping somebody else will pay for it. Whereas ours, we're just using a Dyson vacuum cleaner. It's cheap. You still have to have an infrastructure, but that infrastructure is now based at a refinery or a chemical plant which is doing the recycling. It's a different problem. It's a much cheaper infrastructural problem.
But I could imagine that the recycling is a complicated system,
reasonably,
isn't it?
Yeah. It's a nasty chemical process, and you wouldn't want to do that in a place where there's lots of people.
So it's based like a factory.
A petrochemical refinery would be perfect. It has the energy, it has the steam, and a lot of the infrastructure that you would need to do it. So you could imagine the petrochemical industry, getting involved using the same kind of infrastructure they have now and the same distribution networks that they have now.
So you could say, well, the idea is to have a perfect storage because it's lightweight and it has a lot of hydrogen in it.
Yeah.
But you couldn't store it yourself. I couldn't say, well, I need a storage system for hydrogen in my cellar because I'm producing hydrogen in my cellar. That wouldn't work.
No, you couldn't. You could if you use these other kind of systems. So you can imagine cartridges. You could go to any kind of store or gas station and buy a series of cartridges which you could use in your house. And so that kind of distribution system we could imagine. And the kind of applications we're thinking of for the cartridge system would be a range extender for a vehicle, or hydrogen co-combustion, where you feed a small amount of hydrogen into a diesel engine to clean up your particulate emissions. And there you can imagine a distribution company, a logistic company, taking that out and selling that in a retail kind of way.
That's an interesting point, this co-combustion. So in a normal diesel engine, you have a lot of nanoparticulates coming out, and a lot of sulfur coming out, and other things. You can make this burning process much more cleaner if you add hydrogen to it. Is that true? Yes. So
yeah, feeding around about 3–5% hydrogen on average into a diesel engine reduces your particulate emissions dramatically, particularly at high load. So when you put your foot down the accelerator, an old diesel engine, you get a puff of smoke out of the back of the car, about the vehicle. We can clean that up. So you have to change the engine management system slightly. So it means a reprogramming. You need a piece of kit in the back of your car with the cartridges in, and then that would last you a week or more, depending on the size of your vehicle. And so we can imagine fleet vehicles, like taxis or buses, having this system, enabling them to get into low emission zones, like in London, where these old vehicles that are non-Euro 3 compliant have to pay quite a large premium to drive them at the moment.
And there's another, premium market, you would say, which is
this one,
this model over there.
Yeah, I mean, this is probably our first market. We've been looking at markets where we could sell our material in, at the highest possible price, because obviously it's a new technology, and we need somebody who's willing to pay the prices that we can make it for at the moment. So unmanned aerial vehicles. Initially, it's a military market. This is a military unmanned aerial vehicle, or a model of one, used for surveillance. Camera in there, and it can fly. So with our system in here, with static pellets on little heaters, we have systems that can give you 3 times the range of a lithium-ion battery. So that means you can fly for 3 times longer or 3 times further. But for us, the excitement comes because these markets are going to become civilian. So the aviation authorities are changing the regulation the year after next, and these are set to move out into agriculture, into marine, and security, first responder, survey, all sorts of new markets, and we can sell into that at a high price.
You still have to heat up the pellets.
Yes.
That they give free the hydrogen.
That's right.
And but that's easy done, because it's just each pellet has its own heater, is it?
Yeah. So you
can see it up there.
So you have in here you have a printed circuit board. And on each station, there's a small heater, a very small nichrome heater.
Like a cigarette lighter behind it.
Exactly. And each one, as you heat it, it burns through a single pellet. And when that pellet's finished, it fires the next one, and then the next, and then the next. And in this particular case, the fuel cell fits in the side of the aircraft there, and powers the aircraft. Yeah. It's hybridized with a small battery just to get takeoff, but most of the power comes from the fuel cell. And what we like about it, 2 things really. One is because the pressures we're using, the hydrogen pressures we're using, is so low, we can package it into any shape. So just to show off in here, we've made our first ones packaged into the wing. All right, it's not actually necessary, but it shows the ability to do it. And secondly, our material is stable. So if you have a series of wing sections stored somewhere, then they'll stay with the hydrogen in it for as long as you like. And when you want to use it, it's available. It's stable at room temperature for as long as you like.
Okay. This is just the model.
Yes.
This could not fly, but
no.
It's one-to-one model, isn't it?
It's a one-to-one model, and the real one we're not allowed out of the United States.
So it's a military object.
It's a military object,
okay.
And it's worth $250,000.
Okay, so that's what we call drones. But I couldn't believe that it's such a big market, drones. Maybe a premium market where you can earn a lot of money. But what will the future market? I have heard about Amazon delivering packages with little drones in the future.
Yeah, DHL are way ahead of Amazon. They're already flying it as a test in Bonn, delivering pharmaceuticals around Bonn. But the aviation authorities have stated that they will not allow the use of unmanned aerial vehicles in built-up areas for a few more years yet. The first markets will be agriculture, So you'll be surveying crops to make sure that, when they're ready for harvest. One market we're working on, which is really quite powerful for us, is surveying transmission lines, so power transmission lines. Currently in the UK, you have to survey them every few weeks. You use an infrared camera in a helicopter. It's incredibly expensive. So there are various different firms who are developing unmanned aerial vehicles that every week, every 2 weeks, you fly them across all the transmission lines in the UK, measure them for hotspots, and we would like to sell power supplies into that market.
I would like to give you the opportunity to ask your questions. If you have some, just raise your hand. I'll be with the microphone right with you. If not, I would like to ask you about consumer electronics. Could we imagine to have consumer electronics with batteries made from your material?
Our material, potentially yes, but we have talked to companies who are doing that, and there is a kind of an open call out from Apple at the moment because they're interested in this kind of technology and have patents on the fuel cell and control side. But our material is really good as a lightweight power supply, not a compact one. It is compact, but it's not as compact as they require. So we've aimed for mostly aerospace
because
markets.
It's lightweight,
it's so lightweight, yeah.
There you really can use it.
We think that's the main first market out there.
First market. Latest market will be a complete new infrastructure with your nano composites.
That's right. I mean, ultimately, we want to go from the small scale to the medium scale, which we think we can do fairly quickly, and then in the future go to the pellets and the large scale systems.
Because you want to sell the material which you could produce in large scales, can't you?
Exactly.
Perfect. I would like to thank you very much. We are running out of time, unfortunately. Have a closer look to this model and have also a closer look to the booth of Cella Energy, which is C33, just down the left row here. You find Cella Energy and you find Professor Bennington there. Thank you very much for this talk. Thank you very much for your attention.
Thank you very much.